Good afternoon. I hope you all just enjoyed watching that photo shoot. I am Mike Solomon, Dean of the Graduate School. It's my great pleasure to welcome you to this year's Henry Russel Awards program and lecture. This is a very special event on the university's calendar. It's a day that we honor a colleague with the highest distinction that this institution can bestow, the Russell Lectureship. The 2020 Henry Russell Lecturer is Stephen Forrest, whom Acting Provost Collins will introduce to you shortly. To begin, I'd like to share a brief history about the namesake for the Russell Award. Henry Russell earned 3 degrees from the University of Michigan, a Bachelor of Arts degree in 1873, a law degree in 1875, and then a Master's of Arts degree in 1876. Russell was born in Detroit and remained in Michigan after graduation, where he was a successful lawyer and prosperous businessman who was involved with the Michigan Central Railroad, Michigan State Telephone Company, the Union Trust Company, People's State Bank, and the Detroit Steel Products Company. He was quite the entrepreneurial graduate of the University of Michigan. In February of 1920, while in New York City, Russell took ill and died at the age of 67 from pneumonia, just as he was preparing to travel to Europe upon the death of his son. Lieutenant William M. Russell had been killed in aerial combat during World War I. In his will, Henry Russell left the University of Michigan a $10,000 bequest to create an endowment fund. His one stipulation was that income from the endowment should be used for additional compensation to members of the instructing staff. In May of 1925, the Regents established the Henry Russell Lecture as a way to recognize a senior member of the faculty with an honorarium of $250 funded by Russell's endowment. In addition, $250 was dedicated for an additional award to honor a faculty member below the rank of professor for a conspicuous service to the university. Although the funds from Russell's bequest have long ago run out, the university continues to honor its most accomplished faculty with the award in his name. I am honored to be involved in today's ceremony to recognize these outstanding faculty members. Acting Provost Student M. Collins will present the Henry Russell Awards to 4 faculty members.
Thank you very much, Dean Solomon. It really is a pleasure to be here, being able to recognize the distinguished work of some of our faculty is really one of the great pleasures of this university. And so it's a pleasure to be here with all of you as well. To get started, I would like to invite Professor Cary Ferrario to please come up and join me while I read the citation. Neuropharmacologist Cary Ferrario is known for her pioneering research on the neural and behavioral basis of obesity and drug abuse, including how a prolonged state of obesity alters neural function in reward areas of the brain. As part of her research on the neurobehavioral changes that drive overeating in early stages of weight gain, she examines how food seeking and eating differ in obesity-susceptible and obesity-resistant populations. She also studies the effects of cocaine on the function of brain reward circuits. Her goal is to provide foundational evidence upon which treatment and prevention strategies for obesity and drug addiction can be developed. Professor Ferrario is a principal or co-principal investigator on 4 National Institutes of Health grants. Professor Ferrario has helped to design new neuropharmacological courses and launched the popular interdisciplinary Drugs of Abuse seminar series, where graduate students and postdoctoral fellows present research and discuss advances in the addiction field. She is a dedicated teacher, a faculty ally for diversity and graduate education at the University of Michigan, and recipient of an undergraduate research opportunity program Outstanding Mentor Award. Congratulations for that as well. Among other honors, she has received early career awards from the American Society for Pharmacology and Experimental Therapeutics and the Society for the Study of Ingestive Behavior. Professor Ferrario, in recognition of your exceptional contributions to obesity and addiction research, to teaching and service, the University of Michigan is pleased to present you the Henry Russell Award. Congratulations. Thank you. Congratulations.
Thank you.
And now, will Professor Xiang please join me while I read the citation. Space physicist Xiang, a world leader in planetary physics, combines numerical modeling and satellite observations to study the fundamental plasma processes in planetary environments. He has improved modeling capabilities for space weather research and has advanced the search for extraterrestrial life with his work on the physical conditions of subsurface oceans on Europa and other moons of Jupiter. Professor Jia is a major contributor to the National Aeronautics and Space Administration's interplanetary Europa Clipper mission. He is deputy team leader for the magnetometer team and co-investigator for the plasma instrument that will characterize the thickness of Europa's ice shell and the salinity and depth of its subsurface ocean. He also is co-investigator for multiple instruments on the European Space Agency's Jupiter Icy Moons Explorer mission, which is scheduled to launch in 2022. An aspiring teacher, Professor Jia introduces students to leading space weather forecasting tools, teaches them to run large-scale simulations, and engages them in original research. He also shares his passion for planetary science through media interviews, documentaries, and collaborations on musical and television productions. And I have to say, when I enjoyed his special launch tie, which I hope some of you will have a chance to enjoy as well, that was just an example of, I'm sure, the energy and engagement that he brings to all of the work that he does. Among other accolades, Professor Jia has received a NASA Early Career Fellowship, the College of Engineering Ted Kennedy Family Faculty Team Excellence Award, and a University of Michigan Research Faculty Recognition Award. Professor Jia, in recognition of your pioneering contributions to space physics, your teaching and your service, the University of Michigan is pleased to present you the Henry Russel Award. And now will Professor Karina Schindler please come forward and join me at the lectern while I read the citation. Synthetic chemist Karina Schindler is an internationally recognized scholar for her pioneering work in the development of new and sustainable organic transformations. Among other contributions, she discovered and developed catalytic carbonyl olefin metathesis reactions that rely on iron and make breakthroughs in the related area of oxygen atom transfer reactions. Professor Schindler focuses on an important class of chemical reactions in which double bonds are broken and made between carbon and oxygen atoms, causing atom groups to change places. Her discoveries challenge existing dogma regarding carbonyl-based metathesis reactions and are expected to influence organic chemistry for years to come. Professor Schindler, a Golden Apple Award nominee and recipient of a Camille Dreyfus Teacher Scholar Award, is an outstanding teacher and mentor. And among other initiatives, she updated Michigan's introductory organic chemistry course with new study tools and enhanced discussion sections. She also is actively involved in females excelling more in math, engineering, and science. Nationally, she serves on the Organic and Biomolecular Chemistry and Cell Press Physical Science editorial boards. Among other honors, she has been recognized with a Presidential Early Career Award for Scientists and Engineers, a Packard Fellowship for Science and Engineering, and an American Chemical Society Award in Pure Chemistry. Professor Schindler, in recognition of your innovative work in modern synthetic, organic, and organometallic chemistry, your teaching, and your service, the University of Michigan is pleased to present you the Henry Russel Award. Congratulations.
So much.
And now will Professor Megan Tompkins-Stang please join me at the lectern. And I have to say that this award has a special place in my heart because not only is Professor Tompkins Xiang, a colleague in my home school, the Ford School, but while I was dean, I was the one who brought her to Michigan. And so I'm delighted to help to be able to recognize her in this way. Public policy scholar Megan Tompkins Xiang is an expert on how private philanthropy influences public policy. Her book, Policy Patrons, Philanthropy, Education Reform, and the Politics of Influence, is a landmark study of how elite philanthropic foundations have shaped K-12 educational policy in the United States. The book has received scholarly acclaim and shaped contemporary critical discussions about the role of philanthropy in a liberal democracy. In Policy Patrons, Professor Tompkins Xiang offers a rare glimpse into the internal decision-making of 4 of our nation's largest foundations. She shows how the foundations behave as policy entrepreneurs, as central architects of change initiatives, and through approaches that yield strategic control to grantees. She has received several national awards for her outstanding research and has given numerous lectures in Asia, the Middle East, Europe, and the United States. A passionate teacher and faculty lead for the Ford School's public and nonprofit management concentration, Professor Tompkins Xiang encourages students to think critically about normative questions in nonprofit management, the ethics of public service, and the relationship between philanthropy and inequality. She received the 2018 Provost Teaching Innovation Prize for her experiential course, Private Foundations in the Public Arena, in which students collectively engage in actual grant-making. Professor Tompkins Xiang, in recognition of your pioneering research into how philanthropy influences public policy and education, for your research and your service, the University of Michigan is pleased to award you the Henry Russel Award. Congratulations. And now it is my great pleasure to invite Professor Stephen Forrest to come forward while I read the citation. Engineer and inventor Stephen Forrest is renowned for his foundational contributions to optoelectronic integral circuits and organic semiconductors, which have revolutionized the way we communicate, share information, and produce energy. As the University of Michigan's Vice President for Research, he helped bring new technologies to market and significantly expanded Michigan's research portfolio. He launched the Energy Institute and Mobility Transformation Center, the forerunner to MCity, among other initiatives, and he enhanced economic development as chair of Ann Arbor SPARC, and through his service on the Michigan Economic Development Corporation Board. Professor Forrest holds almost 340 U.S. patents and has helped found 5 companies. He demonstrated the first avalanche photodiode for long-haul fiber communications, a semiconductor device that converts light to energy, and invented the first reliable photodetector now used in almost every fiber telecommunications system worldwide. He developed thin-film semiconductor organic light-emitting diodes that enable flat panel displays in smartphones, pads, televisions, and other applications. He also has advanced the use of thin-film material to produce a new generation of inexpensive, energy-efficient solar cells. An exceptional teacher and mentor, Professor Forrest has chaired or co-chaired 60 PhD committees and mentored 34 postdoctoral fellows. He is a member of the National Academy of Engineering, the National Academies of Sciences, the American Academy of Arts and Sciences, and the National Academy of Inventors. He has also received the University of Michigan's Distinguished University Innovator Award. Professor Forrest, in recognition of your numerous research contributions, exemplary leadership, outstanding teaching and mentoring, and entrepreneurship, the University of Michigan is truly honored to present you with the Henry Russel Lectureship. Congratulations. Well, please join me in welcoming the 2020 Henry Russell lecturer Stephen Forrest, who will speak on carbon versus carbon dioxide, using carbon-based organic electronics for a more sustainable planet.
Thank you.
The floor is yours.
Thank you so much, Provost Collins. Well, thank you for all being here. This is a tremendous honor for me, obviously, and it's a tremendous honor for my students as well, who've helped all this time to bring us to where we are today. So today, what I'm going to talk about is my little bit strange title, Carbon versus Carbon Dioxide. It really centers on a field that I have been exploring since a long time. And it flows very nicely into something that the university is doing today, which is seeking a path toward carbon neutrality. And this is also a problem that I have been concerned about for decades. So I want to start my talk by just giving you some background about where we sit as a planet. Most everybody here knows this because they read the newspapers every day, but this kind of encapsulates it. This in the next slide, which shows what the International Panel on Climate Change sees and recommends. And the current annual emissions are about 52 gigatons of CO2 annually, and they're headed to even higher numbers. However, and I will show you the consequences of not getting this under control, their target of getting to only 1.5 degrees of climate temperature increase by 2030 requires that we be at the 25 to 30 gigaton level. So we're going in the wrong direction today. And by mid-century, we're supposed to basically be at zero. So these are just numbers. They're large quantities. It's very hard for us to comprehend. I think this might help us a little bit more. This shows the consequences of what happens at 1.5 degrees and what happens at 2 degrees, which is probably a more realistic place where we're heading. So 2 degrees doesn't sound too much in human terms. But for the island nations of the world, even 1.5 degrees is life-threatening. It's an existential threat because of the rise in sea levels. You can see the one that always stands out to me, just kind of bursts out of the list, is at 1.5 degrees, we already sacrifice 70 to 90% of our coral reefs and their ecosystems. At 2 degrees, we've lost 99%. That just gives you a sense of all the consequences of climate change, why this is the most urgent problem for humanity today. If you're not sentimental about human beings, that's okay, and we can allow this to grow to whatever it grows to, right? But I think most of us are fairly sentimental about being human beings, and we want our children, our grandchildren, our great-grandchildren to survive in a wonderful environment and have all the benefits that we have. So now let's take this back one step and think about what can we do about it, because when you look at that level of daunting challenge, the CO2 emissions are just rising when they should be falling, et cetera, et cetera. What can we do? And of course, I'm very honored to be the co-chair of the President's Commission on Carbon Neutrality. I co-chair it with Jennifer Haverkamp. I'm very honored to be part of that because the University of Michigan, when it does something and when it says something, it's taken very, very seriously. And as a model for the world, we can do a lot. But of course, then you start to feel, oh my goodness, is this even a feasible problem to tackle? And yes, it is. There's a lot of things going on today that really give us a great deal of hope. Conservation, and I'm going to talk about the two things that in the next two panels will be the core of my talk, because ultimately I'm a technologist. I'm not a politician or anything like that. I'm not an environmental scientist. But conservation is the simplest route to carbon reduction. So we just stop using so much energy, right? We're stuck with a world that produces energy at a certain rate by fossil fuel means primarily, what can we do? Well, if you just look at lighting and associated electronics that we use, but lighting itself is about 25% of the electricity use in buildings, give or take. Residences less, industrial locations more. So I'll talk in the first part of my talk about lighting and what we can do there. And the second part is, how about let us generate electricity in a renewable way which does not require fossil fuel or carbon emissions. And I just wanted to show this. It's a solar opportunity because I think that ultimately good business leads to the solutions that are going to be implemented at scale. And solar is coming along very, very rapidly. It is in the U.S. today is the largest fossil fuel producer in the world, not just user, but we're also the largest fossil fuel producer. So you would think that we have very cheap fossil fuel energy. Well, it turns out that the cost of solar in most locations in the United States is cheaper than fossil fuel. The type of capital you may have to produce to build a solar farm can be problematic, can be a barrier, but once you got it, you have cheap energy. This is one of the projects that's going in. It was announced in the Los Angeles area, 400 megawatts of capacity with about 4 hours of lithium battery storage, so that when the sun goes down, which it has a tendency to do, you'll have still 4 hours of energy that can supply power at 2 to 3.5 cents per kilowatt. And it's currently about 1.5% of the U.S. electricity in solar. It's because the sun does go down. It's actually quite a bit more than that during the day and during the peak hours when we use it. But the business is growing at 30% per year. For decades it's been doing that. And it's getting to be quite sizable today. So, the first thing I'm going to talk about are organic light emitting devices for displays and lighting. The reason I threw in displays here is because I'm passionate about displays. I'm passionate about OLEDs. And by the way, they can be used for lighting, very efficient lighting. And that was that big chunk of energy conservation. So OLEDs are really today revolutionizing the human-machine interface. They're dominating mobile and soon monitor and TV markets, so you can buy them today, OLED TVs, and if you do, you will be very, very happy with what you buy. And so the next question is can they revolutionize the cost and uses of efficient lighting? And I will tell you what an OLED is in detail in a bit. I have a crooked view graph here, but it's coming up, but it's okay. We'll get the point across. Somehow this thing flipped. This is the growth of the thing that you see on that's turned on its side is really the size of the OLED display market today. It's about a $20 billion market. It's quite large, and these are OLED displays, and this forms the foundation of the most efficient light-emitting device that we know of today. And they're everywhere. I have my good friend and partner here, Mark Thompson. We were discussing how many Samsung phones have been made so far. I have 2 billion. It always reminds me of the old McDonald's, signs 2 billion sold. I think we're thinking it's right now about 3 billion. They're everywhere. And they make TVs and so on. So this became a real kind of foundation of OLEDs for lighting, and I'll show you why in a minute. And they're everywhere. I just took this picture at Seoul Incheon International Airport. It's a gigantic OLED display. You can see here. These are, I like to call them scale bars. They're about 2 meters high, maybe a little less. And you can see the size of that OLED display. And that's a very small OLED display compared to which you can find in Abu Dhabi and places like that. And of course, LG makes those, and they're the quintessential marketers. For those of you old enough to know about Kodak moments, LG has made an OLED moment. You stand at this place and take pictures of their displays. Some of the features is that they're roll-up, so you can very soon, actually I think it's this year, LG is introducing a TV that rolls into a little box. You can do lighting, which I'm going to talk about in a minute. Okay, so let's take a step back. What are organic electronic materials, and what do they do that common inorganic semiconductors, that's silicon, gallium arsenide, why are they there? You know, we got such good semiconductors out there. This is what are organic molecules that form the basis of the electronics that I've been working on for now about 35 years. They're basically carbon-rich compounds, and they're everywhere. Everybody in this room, I think, is probably wearing clothing that has organic dyes, and those organic dyes very often are semiconductors, and sometimes very good semiconductors, so very good electronic materials, and they come in individual units as monomers. This thing is about a nanometer across, maybe a little bit more. You can string these monomers into a long chain, and they become polymers. We know those as plastics, very tough, flexible. And then there's us, biological organic things. So these guys are mostly made in the lab, though they do have non-biological origins, and you can even find many of these molecules, not this one, I wish we could, but out in space. They've been identified, and sometimes we get a rock that comes down from Mars, and people say, oh, it's got organic molecules like anthracene in it, there must be life on Mars. No, it can be synthesized quite inorganically, if I can use that word. This is too complicated for us. We don't know how to build these things, but they're fantastic solar cells very often. They're called plants. Photosynthesis. So what makes organics different? I'm not going to talk about biological molecules. I'm too sentimental about them. I'll talk about the others. I'm not going to go through everything here, but I just want to point out the big difference between organic materials and semiconductor materials is how they're bonded, how they assemble themselves into a solid. And the way organic molecules assemble themselves into a solid is they're electrostatically bonded. There's no chemical bonds between those molecules within the solid. They just kind of stick together electrostatically. In inorganic materials like silicon, the neighboring silicon share electrons, and they form a chemical bond. And from that essential difference comes everything else. All their optical properties, which I'm going to talk about next, and all of their electronic properties. Some of them are very good, and some of them make them very poor semiconductors. You would never, for example, use an organic semiconductor to replace, let's say, the 5 billion transistors that are in the central processing units of your computers today. It wouldn't function, it would be too slow, it would be a mess. Actually, there's pressing toward 1 trillion transistors in your little machines today. So you should be happy you have so many things at such a low price. So the essential optical difference is because of this electrostatic bonding, the electric fields within these materials is quite low compared to, let's say, a regular semiconductor, or actually quite high compared to a regular semiconductor. And so what happens is that when you bring in light, you create an excited state, and that excited state, it's basically an electron gets promoted to a higher level, and then eventually it decides to recombine, that is, come back down to its lower state and give off a photon, and therein generates light. In inorganic materials, this excited state is it's spread over many, many atoms in the lattice, maybe 50 or 100. But because of this electrostatic bonding that goes on in organics, each organic molecule forms its own excited state. You put electrons onto that molecule, it will get into that excited state. You wait a little bit, and with very high efficiency, 100%, you'll get light out. So it's a really active optical and electronic material. And that's why we use them as dyes in our clothing. We use them as in our inkjet printers and laserjet printers. Those are all organic semiconductors, very heavily colored. So why should we care about them? Well, because they're so, they can go onto your clothes and so on. They can be put over huge areas. And things like displays and lighting and solar cells are large area devices. They can be extremely low cost. They can be expensive too, but largely speaking, they can be very, very low cost. And they are produced at very low energy. So the payback time for, let's say, a solar cell can be quite brief. They can be put on flexible substrates. Polymers already are organics. Well, we can make devices that roll up and form onto any shape you like. Conformable. If you buy an Audi today, you probably have an OLED tail light on it. It's been shaped. They like that. Easy to manufacture, and they're everywhere. Good things. So, my mantra is if two or more of these conditions are met, the case for organic electronics is highly compelling. And we like to think about organics the way we think about newsprint. After all, newsprint uses organic dyes and inks to make the images that we see. And it's made on rollers, very, very fast, at extremely high rate. Well, what if we could make electronics on a roll-to-roll process? And we do that. So let's now turn to the light emitter, turning molecules into very efficient displays and lighting. The bilayer OLED was invented by Ching Tang and Steve Van Slyke at Kodak in the mid-'80s. And it's a very thin device. It's only it's about 100 nanometers thick. You bring in electrons from one electrode and holes from another electrode, which is the positive analog of an electron. And they combine on this molecule. They excite that molecule into its excited state. They create this thing called the exciton. And then after a little bit of time, a few nanoseconds, this thing relaxes and we get a green photon out. That was their innovation. It was not terribly efficient, but it was really exciting because you could put in a little bit of current and all of a sudden you had this light emitting device which was far thinner than a human hair. Then you can make an OLED display. I'm not going to talk about that in any detail, but I think a key step forward when things got really exciting was when the process of electrophosphorescence was introduced. The problem with the Tang device is it isn't very efficient because when you send in an electron onto these molecules, only from a quantum mechanical selection rule, without getting into detail, only 1 in 4 of those electrons can actually generate light. The other 3 generate what's called phosphorescence, which we have on watch dials. It's slow, it's inefficient, it's not very much fun, unless you have a watch dial that you want to read at night. But if you want to make a display that moves and everything else, you don't want that. The innovation here was to put a heavy metal atom in the center. Did this with my good friend Mark Thompson. And that broke this quantum mechanical law. So now every single electron that came onto these molecules would emit light. We now had a 100% efficient device. And you can make all kinds of things. It's a miracle of modern chemistry is all I can say. I like to say that blue is beautiful. We've been working on blue for a long time. Sometimes I think it's the ugliest color in the world because there are problems we can't solve. But it's really satisfying to make these things. You can't even see the OLEDs. They're so bright. They're pointing away from the camera. And here you can just see the bare edge of one of those OLEDs going, and we're projecting its color onto the screen. What I like to show this is that this is exactly the same chemical in both cases. The structure is just slightly different. In one case, those rings are kind of on a face, and in the other, one is twisted out of the face, and it makes it a little greener as opposed to blue. And the problem is they're short-lived. Blue is. But we're working through it, and there are solutions to it. So if you have a lighting, I just want to show this chart, since we're talking about reducing carbon in the world, and therefore efficiency is so important. If you still have incandescent bulbs in your house, you should go out there with a hammer today and crash them up. It's a wonderful invention, and the only problem is you got a technology that's 150 years old. I mean, who wants that in their house, right? You can't sell a house with 150-year-old technology, really. But they're very, very inefficient. They're basically a heater, which gives off light as a byproduct. So this has turned around, and now you can buy LEDs, light-emitting devices. So those are inorganic gallium nitride-based devices. They tend to be extremely efficient, and they're actually getting pretty cheap, about $5 per kilolumen. So an incandescent bulb is about 50 cents per kilolumen. Just to give you an idea, a 60-watt bulb is about a kilolumen. So it's about 50 cents for a 60-watt bulb, about $5 for here. But by the time you run this through its lifetime, and you have to replace this one 10 times before you wear out one of these, and you use less electricity, this is actually a tremendous energy saver. And that's why the Department of Energy wants you to buy those things. OLEDs, we're getting 100% efficiency in the device, but getting all the light out is still a challenge. Because it gets trapped inside the device, but we're working on that. There's lots of very good solutions to that. The real problem with these are they're still too expensive, so for architectural uses, they're very exciting. But for common lighting, there's still some work to do. But, you know, it's just like displays. The more you make of them, the cheaper they get. These are just some OLED chandeliers. This one is in Munich, in Deutsche Bank. It's really, I think, one of the prettiest ones ever made. The nice thing about OLEDs is you can make windows that light up and become transparent when you turn them off. And this was a job done by an experiment done by one of my students, Caleb Coburn, who's now at Apple, who uses these things in the iPhones. He's made these very intense OLED devices. There are lots of layers, a lot of thought has gone into this. And they live a good long time, 80,000 hours. So if you think about your incandescent bulb, it's 800 hours, 2 orders of magnitude shorter. Okay, so let me, in the rest of my talk about solar cells. Can they compete with silicon? You see silicon fields, tremendous amounts of them out there. We have some on North Campus. Actually, we have 2 fields on North Campus. But you just drive up in Michigan, you'll see them in the fields. In other states, many more. If you go to Germany, they had to stop the deployment of solar because the farmers were finding it was more economical to build solar farms on their fields because they could sell that energy than it was to graze cows or grow crops. So they came with a law that says you can only fill up 20% of your field with solar panels. I don't know how much that stopped them. They tend to behave, but nevertheless, they really went all in when solar was not very inexpensive. I've already shown you it can be terribly cheap today. And we're going to be talking about using transparency of our solar cells as a ubiquitous source of clean power. And that might seem like a contradiction in terms, making a transparent solar cell. And so I thought it was supposed to absorb light. Well, actually it does, but not where you see it. It absorbs, we can make it absorb in the infrared, where there's a ton of solar energy, but it could be transparent in the visible, so why not make windows that generate electricity rather than just generate heat? Because your windows are cutting out about 50% of the light, somewhere in there, sometimes less, sometimes more, depending on the application. So this just shows an energy diagram. I have to go to some physics here, of what the internal workings of a solar cell are, or the organic solar cell. This is a plot of energy versus distance along the cell. So we're going through a very thin film again. And what we do is instead of generating a photon by making an excited state or exciton recombine, we're going to take a photon, bring it in, and excite the material. And then we're going to let that excited state hop from molecule to molecule to molecule until it gets to an interface between a donor material, an electron donor material, an electron acceptor material. The electron wants to lose energy, so it pops over to here. The hole wants to lose energy. It pops over to here. It kind of does it in the opposite direction, but it's a little bit subtle. But the fact of the matter is we can, with a very high degree of probability, turn a photon into a free charge. That's the opposite of light generation, where you take a free charge and you make a photon. So that's a solar cell. Okay, just some facts. Is there really enough solar energy? You bet. Everything on Earth we owe to the sun. Everything. There's not a single thing here that did not come from the sun at one time or other, from nuclear to whatever. But every day we get a lot of sun, even in Michigan. And actually Germany, which has gone whole hog, it doesn't anymore, but it did go whole hog on solar installations, has probably fewer clear days than Michigan, although we are really in a bad spot for sun. But on a sunny day, we get about 1 kilowatt per square meter of sunlight. And now this is a round room, so I have trouble dealing with it. But, it's probably, what, about 150, probably about 50 meters, right, by 50 meters. That's, what, 2,500 square meters? That's 2.5 megawatts hitting this thing. That's a lot of energy. We just got to figure out how to get it cheaply. These are the efficiencies of solar cells that are out there today. This is called the technology readiness level. So just to level set you, those solar fields you're seeing out there are probably on the order of 20% efficient, which means for every square meter, they're getting 200 watts of power. That's probably what's going on up on North Campus. The highest you can do with a single junction cell is about 30%, but it's a very expensive technology based on gallium arsenide. Organic solar cells are sitting at about 17%, 170 watts per square meter. That's really good if you think about it, especially since these are super cheap. But as I often tell my group, if you're going to compete head-to-head with silicon, go home, you already lost, because silicon is such a embedded, mature technology. So we have to do something very different. So let me go to organic solar cells. The same character at Kodak in 1986. Oops, go back. Now you guys know what I'm going to say. That's embarrassing. All right, I have to do it this way, the old-fashioned way. There we go. Same guy, Jing Tang. The year before the OLED, came up with an organic solar cell. He put it in front of a Kodak carousel projector as a solar source, and he found it was 1% efficient. That was really exciting to me. That actually changed the course of my research completely. I had some friends at Bell Labs before that who we worked on organics with together. And the year after this, he came up, Jing Tang came up with the bilayer OLED. And I got a call from my friend Paul Schmidt, who I'd worked with for years. He's an older gentleman. And Paul said, Steve, you have to drop everything and start working on OLEDs. They didn't call them OLEDs in those days. And I says, I can't. He says, why not? I said, because I'm working on his earlier paper right now. And that was this one. It was just such a beautiful paper. And my first solar cell that came out of my group came a year or so later. It's been paced basically by the efficiency. Of course, 1% is terrible if you saw that chart, but that was the first demonstration. It just showed the possibility, and it's been mostly paced by new materials. Right today, the materials are getting very sophisticated. We engineer them in my lab, but to tell you the truth, the Chinese laboratories have tremendous lead in the development of these types of materials. We call them acceptor, donor, acceptor materials. It's a lot of detail. The important thing is this is the spectra, the absorption spectra of these materials. Again, some maybe are some other people, but what's interesting is that they absorb, so the visible spectrum that where we see is about between 400 and 650 nanometers. This is what we see. That's our world. Out here is the infrared, the longer wavelengths. And you can see they're rather narrow and they just absorb there. So why don't we choose some materials out here to absorb out there and generate electricity and then build solar cells. So this is a group of materials, uses different optical tricks and so on and so forth. But this is a solar cell. It looks like just a piece of glass. Some of you who have journeyed far today will recognize this area. I guess that's what Dow. Yeah, I think it's the Dow building. But you can change the color of these things. I don't think you really want a window that looks like that, but this thing is really efficient. It's not this. This is when it's opaque, you get up to about 13% with these types of materials. This is what's called a chromaticity chart, and if you want a window that looks really neutral density, there it is, right in the center, and that's one of our devices. We have a characterization for transparent materials, which we call the light utilization efficiency. It's basically the power conversion efficiency times how transparent it is. And right now, our lab is sitting up here at about 7%, or no, actually 5%. I'm sorry, I'm looking at this kind of at an angle, about 5%. And then this is the rest of the world. These things really are looking exciting for window applications. So you hang up a window. Of course, it's not going to have exactly the right profile for the sun, but it's going to generate a lot of electricity during the day. We have to figure out how to get that electricity in your window integrated into your household electricity, and it's not very hard to do that. You integrate these little what we call mini inverters on them and so on, and we've been looking at the economics of that. It looks very, very, very interesting. A lot of things that people worry about is organic molecules are fragile and die. Because we know that because we're fragile and we die. And we're organic, right? But in fact, that doesn't have to be the case. Your OLED displays last about 1 million hours. A year is 7,000 hours. So if you stared at your display for 7,000 hours, well, nobody in this age group would want to do that. But if you stared at it for 7,000 hours, you would have spent a year of your life looking at a screen. So keep your kids away from so much screen time. So that's one of the things, but we've been playing around with some devices that we find extrapolate out to 27,000 years. That's a long time. Of course, when you put it outside, it's not going to live that long. This is an intrinsic lifetime, but it tells you that there's no reason to think that organic solar cells can't last as long as inorganic. I sent one of my students out to Israel. They get a lot of sun in the Negev desert with very few clouds, except when we were doing our experiment. And this is what happened on this day. So this is the thing just running out there in the field for 100 and some odd days, and then bang, it just died. That day, he said it rained in the Negev desert. So we have packaging issues to do. So I want to end this talk with one thing that I saw when I was out in California, and I think it's a really important saying, is we do not inherit the earth from our ancestors. We borrow it from our children. And I think that's really the wisdom that ought to be driving us today. We're so interested in consuming everything around us, but really, we're not here for very long. So we borrow it from our children, and that comes from an unknown Native American tribe. With that, I want to thank some people. This is my current group. We call it the Optoelectronic Components and Materials Group. I can say that everything that I say in my talk that is correct, I owe to my students, and everything I say that is wrong, I owe to myself. They have really taught me a lot through my career. The other person who has taught me a tremendous amount is Mark Thompson, my partner in crime and great friend. For 25 years, we've been working on OLEDs, now solar cells, and he has a group of incredible chemists students many of whom I've gotten to know over the years too. So we have this gigantic sort of team of people that just really works together marvelously. Of course, I've had great support from a lot of places. Universal Display Corporation, which Mark and I helped found, is really at the core of the OLED and OLED lighting world and OLED display world. I also owe a lot of debt to the Air Force Office of Scientific Research, who has, and Charles Lee, who just retired, and he funded me for longer than he probably wants to tell anybody in the Air Force Office of Scientific Research without getting into some sort of problem. But he's retired now, so I can say that. And of course, my wife, Roz, who's been with me forever in a fantastic journey. So thank you all very much.
If the speaker, we have some time for questions, and we'd ask you to use the microphone for them.
Hi, my name is Asan. I'm from Mongolia. I'm not a tech person or engineer or anything, just a simple question. I know energy is a huge problem worldwide, and developing countries are suffering from the effect of climate change a lot. And can this technology not only provide, light, but also like heating, heating as well? Because lots of air pollution is caused, by burning fossil fuel and, even in the households. So, and millions of people are dying in developing countries because of that.
So I think that developing countries have an opportunity to not make all the mistakes that the more developed countries have done. These technologies can be very inexpensive. That's the point. So it can be less expensive than current technologies, and it also allows you to generate power at the location that you live in. And so, for example, I love this, something called Light Up the World Foundation, and they started supplying solar panels with LED lights to families in India, in truly rural, impoverished places. And what was their cycle of life every day? It was to get up with the sun, work in the fields, come home, and when the sun went down, they'd have dinner and go to sleep. So their day was sort of leveled by that. What they found is if they could just supply a solar panel, a small solar panel, and a LED light, what happened is the kids particularly started to read, because after hours you read, right? That's what you do when you have a light in your house. So that now breaks that cycle, because the literacy now gets to spread. So in those days when that program came out, maybe 15 years ago, 20 years ago, things were not as cheap as they are today, but they're very cheap today. And there's a lot of schemes to put solar into people's hands, even if they have almost no income, because you can have them pay as they use it. And you have to be kind of clever about how to do that, but that's what's starting to diffuse. And I think, and China right now is one of the largest rapidly growing markets for solar, and they've invested a huge amount in it, which is one of the things that has driven the price so far down. Sometimes it happened by government subsidies, and then American companies and other companies decided, well, if that's the game, we better start to play it. So they brought their prices down, and they'll never go up again. So I think there's a lot of hope for remote places to get electricity and lighting where they've never had it before, and this is one of the technologies we're working on.
I'd like to put some kind of solar electric system on my house. How long do I have to wait to be able to use this kind of technology instead of the standard silicon panels?
I have a house in Vermont, and people ask me all the time, why don't I have organics in my house, organic solar cells? And I tell them a little bit snarkily, I want to have power. These are still a little bit, so I use silicon, and it actually was very inexpensive to do. You know, you set it up, there's an upfront cost, and because I'm off-grid in my house there, I have no choice. So I don't get any subsidies from the state because they know I need it. Okay, so when we set it up, you have a setup cost, and I would guess the payback time is about 5 years. But once you set it up, there's very little expense. You know, we have batteries. That's how we do it. The stuff that we're working on in the lab, it's laboratory stuff, right? And we have industrial partners, and it takes a bit of time. When we started on the OLED journey, it was 1992, I think something like that. By the time and we started our company in 1994. We went public in 1996, had almost nothing. And by 2006, we actually started to make money. So it takes time. People say things happen more rapidly now. I don't believe that. I think it still takes 20 to 30 years between an innovation and a deployable application. So these windows, you know, we're talking to glass companies and things like that. It's, I think you're looking at 5 years. It's pretty much the deal.
Last question.
Exciting. Thanks, Steve. That was awesome. I'm just kind of curious. A lot of the criticisms I often hear is that a lot of times the burden of reducing climate change or fighting climate change falls on like individuals, where it's like, you know, put new light bulbs in your house or eat less meat or bike to work, when in reality it's a lot of times corporations that are contributing the most to climate change. So I'm curious, what do you think about like this kind of technology for, you know, can it impact corporations to maybe do more on their end to lessen their carbon footprint, or do you think there needs to be much bigger, wide-sweeping changes in order for that to have an actual impact?
That's a very complex question. Companies are purely driven by money. So if they see that there's a buck to be made, they will go and find it. And this is becoming a very profitable business. So that's one of the things that helps. On the other hand, there's vested interest, right? A company who's selling one thing doesn't want to change and very often gets swept aside. You know, I like to say that there's such a thing, there's people out there who are climate deniers, climate change deniers, and I tell, my basic feeling about that is there's very, very few, because most of us wake up in the morning, we have something in our head and we read, and we can see the world around us changing. Climate denial is a proxy for vested interest, okay? So all we got to do is show them where the bucks are, and they will follow that. On the other hand, so the complicated part of that is that corporations left to themselves follow different they have a different DNA. And so what you need is the government to provide some guardrails, to make sure that you stay in the lane and that you provide also some incentives so that these companies will find their way to shift their direction. And you're seeing that everywhere. But, you know, our big corporations in this state, Ford and GM, they already have carbon neutrality plans. Why are they doing that? Well, two reasons. There's actually money savings, and the other thing is their customer demands it. And if you don't, and you know, we have customers too, they're called students. So if we don't, if they deny that, they're not going to exist. And they're into the survival thing, you know, just like all of us. So the world is changing very, very fast right now in its attitude toward how to fix these problems. And there's a lot of technical solutions, but you should never underestimate the power of the individual. If you turn off your light, remember there are 7 billion people on this planet. 7 billion lights go out at night. That's a good thing, right? 7 billion people don't eat as much meat as they used to. I'm not an advocate of changing our lifestyle and living in tents. Okay, I want to live a really nice life, and I want my kids to live that life the same way. I don't think that they are in tension. You can have it both ways. We just haven't constructed our world to have it both ways yet, but we're moving there.
Thank you, Professor Forrest. Please join me in thanking our 2020 Henry Russell Lecturer.